Hello everybody, it's Coach Tapman, and today we're going to be talking about wheel and axle as a simple machine. So what is a wheel and axle? A wheel and axle is a machine consisting of a wheel attached to a smaller axle so that these two parts rotate together in which a force is transferred from one to the other. We can actually look at an example on this next page and get a better idea of what that is. But essentially think of a wheel and axle as a transfer of torque about an axle or a shaft of some sort. In this scenario here, you have this water wheel, and you can see that you have this larger wheel and a smaller shaft that's actually connected to the bucket. Well, if you remember from our lesson on moments and torque, moments or torque is directly proportional to the distance that the force is being applied. So you can see in this example here, you have this large wheel that's attached to your axle. If you apply force on this wheel and rotate about the wheel instead of the axle, it will be easier for you to raise this bucket than if you applied the same force along the axle. And that's just because your distance is greater on your wheel in this scenario than on your axle. And so really that's how it works. The same is true with a water wheel. By applying water, even if it's smaller amounts of water, along the outside rim of this water wheel and moving the wheel, whatever churning mechanism or whatever is attached to the inside of this water wheel will move and because of the applied force along this greater radius of this axle. And so really wheel and axles just take advantage of torque. And so when you're looking at the ideal mechanical advantage of a wheel and axle, it's fairly straightforward. The ideal mechanical advantage comes from the length of your effort arm divided by the length of your load arm. And so for your effort and your load arm, if we go back here to our water wheel example, we'd be looking at the radius of our water wheel, or the user wheel, divided by the radius of our axle. The radius being from the fulcrum for both of those. And so fairly straightforward. Another mechanical advantage, though, that you need to make sure you are aware of for Science Olympiad is also when you're looking at the mechanical advantage for a gear wheel. And so questions that you can sometimes see pop up is, what is the mechanical advantage of converting between two different gears? Well, the assumption that is being made when you're considering these problems is that proportionally the gear teeth and spacing and everything is directly related to the actual radius of these wheels. And it certainly is close to this in real life. It's not 100%. But for problems as such, you can calculate the mechanical advantage for a gear wheel by dividing the number of driving gear teeth, or your effort, divided by the number of driven gear teeth, or your load. And so in this case, we have a driving gear with 60 teeth and a driven gear of 40 teeth. Now this is doing the same thing where it's taking advantage of the difference, or the ratio of distances that the forces are being applied. So if you have a larger gear that your force is being applied to a smaller gear, you would be experiencing advantage. But it's just using teeth instead of a radius, because the assumption, again, is that the number of teeth is directly related, directly proportional to the radius of those wheels. So again, your ideal mechanical advantage for a gear is going to be equal to your number of driving gear teeth divided by your number of driven gear teeth. So now we're going to go ahead and look at an example of calculating mechanical advantage in a wheel and axle.
Now we are going to look at an example for mechanical advantage for a wheel and axle. A well sits on top of a hill. You apply a 20 Newton force to turn the crank handle of radius 0.5 meters. This rotates the axle of radius 0.1 meters, raising the 60 Newton bucket of water. Okay, well, let's see what we learned from this so far. First off, we have a 20 Newton force that we are turning. We are applying a force of 20 Newtons to turn the crank handle of radius 0.5 meters. This word "u" here is very important because that implies effort. And so what we just learned is our effort force, which is going to be equal to 20.0 newtons. And our effort radius, or our effort length, whatever you want to call it, as long as you're consistent, of 0.5 meters. Looking at the next statement, this rotates the axle of 0.1 meters, raising the 60 Newton bucket of water. Well, we can now conclude that because our effort, in this top statement here, U, does work to move this bucket of water that is resisting, we now have our load, or our resistance. We know our force for our resistance is 60.0 newtons, and the radius of our resistance, or our length for our resistance, is equal to 0.1 meters. Well, that's great. We then know from our equation for the mechanical advantage for a wheel and axle, remember our mechanical advantage equation is the length of our effort arm, or the radius of the effort arm, over the length of our load arm or resistance arm, or the radius of resistance, whichever you prefer. Seeing that we have both of these calculated above, we're going to go ahead and plug these both in. Canceling out our meters and doing some basic division, we come to the conclusion that our mechanical advantage for this system is equal to 5. Which certainly makes it more appealing to use the wheel and axle than just trying to lift the bucket up by the rope.